So in section 4.2, we're going to go over a particular exponential function. And I'm going to actually kind of hint at where this came about by looking back at this old formula for compound interest. Hopefully you remember this one. Principal, R is your interest rate, as a decimal, N is the number of times a year that interest is compounded, and T is time. So we're going to look at kind of an artificial example of this. We're going to figure out how much our investment is worth if we invest $1 for 1 year at 100% interest rate. Now, the tricky thing is with this formula is that you've got to convert the percentage to a decimal. And 100% as a decimal turns into R equals 1. So, in other words, I'm making everything 1 here except N. N is the number of times a year that interest is compounded. So let's go over to our decimals link and take a look at that here. So here's the graph of that. And we can do kind of a thought experiment here. And let's see. I am sharing my screen, right? You can see my screen? Okay. I'll trust that you say something if you can't. So if you invest $1 on January 1st, then at the end of the year you get 100% interest, you're going to have $2. So after 1 year, if you compound interest once that year, you'll have $2. But what if you compound it twice a year? So let's put in a 2 here, but before I put in that 2, let's think about it. Halfway through the year, you're going to get half of your interest. 50% of $1 is 50 cents. So on July 1st, assuming you invested on January 1st, on July 1st you have $1.50. At the end of the year, December 31st, you get another 50% interest. 50% of $1.50 is 75 cents. Now you should have $2.25. So I'll put a 2 in there, compounding interest twice a year, and yay, we get a little bit more money back. So this is kind of a fun game. Like, hey, let's compound more often, like maybe quarterly, 4 times a year. So now your initial dollar investment is going to return $2.44. What else can we look at? Well, it would make sense to look at monthly, or this is interesting, and this is true, that daily compounded interest is 360 times a year, not 365, 360. And we can even go to kind of an extreme here of compounding interest 365 times 24. How often is that? That's compounding interest hourly. But the interesting thing is that the amount of extra interest we get kind of slows down. So it started out with, we got an extra 25 cents going from annually to semi-annually. Then we got an extra 19 cents going from semi-annually to quarterly. And then you got an extra 27 cents going from 4 times a year to daily interest. But it slows down a little bit. I guess in between here we missed 12. So you got an extra 17 cents here, an extra 10 cents here. You're reaching a limit, and you can kind of see that when you look at the graph of this exponential function. It kind of plateaus. And that limit plateaus at a special number called E. And you can see we're really, really close to that value of E up here in our formula. And it's the graph of E that we're going to spend some time with here today. So let's play around with that a little bit. Now, just for kind of an FYI, and looking at E, there's the first few digits of E. It's not a rational number, meaning you can't write it as a fraction. We can look at its graph. Notice that it's between 2 and 3 someplace. So if I was to look at the graph of, say, 2 to the x, so y equals 2 to the x, and then y equals 3 to the x, somewhere in between here should be the graph of y equals e to the x. And bam, there it is. So a little bit closer to 3 than 2, all right, to be expected. This has all the characteristics of an exponential function that I highlight. When you get to the right of the y-axis, this graph kind of takes off. It grows exponentially. In fact, if you've ever heard of a viral video, viral videos are videos whose growth explodes like this, exponentially. So it starts out kind of slow and then takes off. To the left of the y-axis, the graph gets close to, but never quite touches 0. So the line y equals 0 is what's called a horizontal asymptote. It never quite touches that line. So in fact, here's kind of a good moment to do a little reminder of something else, and that would be, let's take a look at the domain and range. So the domain and range of y equals e to the x. As far as the domain is concerned, there's nothing that we can't put into this function. Nothing is defined everywhere. So that would be negative infinity to infinity. Of course, you might remember that I like script R as opposed to that. And how about the range? The range, we're going to have to look at that one a little bit closer. So let's see here. Let me shut off this one and this one. And let's make this graph a little bit darker. There we go. So the range is on the y-axis, and we want to list it from top to bottom. So it starts at 0, doesn't get below 0, and goes up and up and up and up to infinity. So it's going to be 0 to infinity for the range. And I'm using parentheses because infinity always gets a parenthesis, but 0 gets a parenthesis as well because it doesn't quite touch 0. Okay. Now, let's play around with some things in terms of this one right here. Some of the things you're going to be asked to do, and maybe you want to do some of this with your calculator, maybe you want to do it on decimals, it's up to you. But some of the things you're going to be asked to do are to calculate values. So here it is on decimals. I defined this function h of x equals e to the negative 2x. I just typed it in as you see it. So there's h of 2. If you wanted to do that on a graphing calculator, you could do likewise. So let's take a quick look at it on our graphing calculator. On the graphing calculator, you need to hit the second key and then the ln key to get to the log functions, or excuse me, the exponential function. So second ln e to the negative 2 times 2, bam, there you go. So that would be our function h of x evaluated at 2, because when you put in a 2 for x, you want to put 2 times 2. You could also just type in e to the negative 4. The nice thing about plugging in into decimals or maybe doing a table is that you don't have to keep on typing in the function again and again and again. So let's take a quick look at it with the table. Most likely in your next class, you won't be using decimals, so I'll type in second ln e to the negative 2x. Make sure you don't use a subtraction key to plug in that negative. Assuming that you have your windows set up okay, that is your table set up, then we can go to the graph key and get anything we want. So for us, we want to figure out the value of this. Let's just delete all these old ones. At 1 divided by 3, 1.5, negative 1, and negative pi. Pi is above the up arrow key, so when I press the enter key, it's going to replace this with negative 3.141592653 5897 or 79, etc. So, all right, I'll let you look at the rest of them as needed, but there you go. If you don't have enough decimals from the y value, then put your cursor on whatever particular y value you need, and then you'll get more decimals than you can use. So, nice. Let's keep going. Let's take a look at some examples and play with some graphs. So let's see here. Ladies? So I already went over this part of it, that's y equals e to the x. What's a graph of y equals 2 plus e to the x going to look like? How is this graph going to be shifted? And right now it's got the three characteristics that I would expect that you know, that it grows quickly, it passes through the point 0, 1, and then the third one is that the y-axis is a horizontal asymptote for this graph. So how is that going to change if I were to look at this graph instead? How is it going to shift? Well, you've got four choices: up, down, left, or right. Which one do you think it is?
Up.
Up? Up is correct. Good. So everything is going to get shifted up by 2. So it'll start with shifting this up by 2. Instead of 0, 1, that's going to get shifted to 0, 3. And then instead of y equals 0, that line's going to get shifted up as well. Where's that new line going to be? How about at y equals 2? So it's just getting shifted up vertically by 2. And then as best we can, we're going to try and draw this graph, that shape, through here. Beautiful. Absolutely beautiful. All right. Looking good. Let's play around a little bit since we've got such a nice graph here. Let's see if we can't figure out the domain and range for this. So we'll start out with the domain. And now we're looking at the blue graph right here. Maybe I should just do this. Underline it in blue, like that. So what's the blue graph going to look like? Or what's the domain going to be? Well, there's really no restriction on the values of x that we put in here. You can put in anything. So it's negative infinity to infinity. And when you look at the graph, it's defined everywhere. Of course, if you move very far out on the positive x-axis, you're going to have to look really, really high up to spot the graph, but it's there. How about the range? Now, keep in mind that this is the line y equals 2. This graph never quite touches that line. So, so the range is going to start at 2 and go up and up and up to infinity. But does 2 get a bracket or a parenthesis? Parenthesis. Well done. Nice. Nice. All right. How are we looking on that one? Doing okay? All right. Well, let's keep going. Let's try this function. So we're kind of turning things around a little bit. In fact, we're going to think about this graph via translations. Now for myself, I might want to rewrite that as negative e to the x plus 5. So all I did was I interchanged the order there. But for me, that's helpful because I can better tell the two things that have happened to this function. Here and here. What's that negative going to do to the graph of our function? So forget the 5. Just concentrate on the negative. What's it?
Flip it over the x-axis.
Good. It's going to flip it over the x-axis. Perfect. So flips it over the x-axis, and then the 5 does what? That's going to shift it vertically. Yeah, up 5. And I think I might have that on Desmos as well. So let's take a look here. Let's see. Yeah, I already did that one. Well, we're going to have to repurpose this one. So I'll put in a minus e to the x and then a plus 5. Actually, I'll do that one at a time. I'll do minus e to the x, so you can see that it flips the graph around the x-axis. And then if I add the plus 5, well, now that got shifted up by 5. So there's our graph. Nice. Let's think about the domain and range again. So our domain, that's pretty much everything. So I'm just going to write my fancy notation, that's script R. What about the range, though? From lowest to highest. What's the lowest that this function seems to get? And I can shut off the graph that's in green because we don't need that anymore. Just looking at the graph that's in kind of a purple, where does that graph start? What's the lowest value it gets to? Negative infinity. And it gets up to, it doesn't quite touch 5. Yeah. Cinco de Mayo. All right. Doesn't touch 5. Perfect. Perfect. Looking good there. You should be able to predict what's going to happen with these translations. So let's come back to our handout, and then we're going to look at the graph of e to the negative x minus 1. I think I might have to adjust this. That should be a minus 1 there. Here we go. So let's start out with the negative here. That's a different kind of change to our function that you didn't have in, say, the previous class, Math 1150, if you came up to this class through that route. What's the negative going to do to our graph? Do you remember? It does something special.
Flip it on the y-axis.
Ooh, spot on. Well done. Yeah, flips it on the y-axis. Thank you. So we'll see that here. We've got e to the x, and then bam. There's your graph flipped around the y-axis. So let me shut that off now. And now that I've made that change, what's this minus 1 going to do to our graph? How's that going to change it? Down by 1. Perfect. So the point that was at 0, 1 should now be at 0, 0. And let's see that. And bam, it's done. It's there. Perfect. So flipped around the y-axis and shifted down by 1. Flipped around the y-axis and down by 1. Cool. Excellent. Excellent. Doing okay so far? All right.
Yep.
Thank you. Thank you. Let's see here. Is this what you guys have next on your handout? Yes? Okay, perfect. So, say a graphing calculator is recommended for this one. We can do it on a graphing calculator. We can do it on Desmos. It works out the same way. Just a little bit more work on the graphing calculator. So let me shut these graphs off and turn this one on. Y equals 3x to the x power. If I remember right, this is called a hyperpower. These functions grow even faster than your regular exponential function, which already grows really, really fast. You know, it might not be a hyperpower. I think you might have to have one more exponent. Not sure. But in any case, it is a really, really fast growing function. And you're being asked for a couple things here. Find the local minimum or local maximum. So local minimum and local maximum, these are points that are kind of lower or higher than any nearby point. So let's take a look at the graph. This graph doesn't really have a local maximum, at least in my humble opinion. I don't count that one as a local maximum. Local maximum is going to be something like, let me come up with one, y equals x cubed minus 4x. This is a local maximum because it's bigger than anything near it, but it's not the biggest thing going. I mean, you just have to move over here and you see bigger and bigger values. Likewise, this is a local minimum because it's lower than anything near it, but it's not the lowest thing altogether. So are you okay with the ideas of local max and local minimums? All right, let me shut that off. Let's look back at this. So what do you think? Is there a local maximum here? I ain't seeing anything. No, it just goes up and up and up and up. So there's no local maximum, so that's a D and E, does not exist. And as far as the local minimum is concerned, bam, right there. You find it that way. So you can also do that on a graphing calculator. It's just a little bit more of a pain. I think I've got some of those how-to videos on a different YouTube playlist if you wanted to look it up. All right, so you could be asked for two things. You could be asked for the x-coordinate or the y-coordinate. So pay attention to what I'm looking for when I ask that. Let's move on down to work with one more regarding the function e. I like this one. A skydiver jumps from a reasonable height above the ground. The air resistance she experiences is proportional to her velocity, and the constant of proportionality is 0.15. It can be shown that the downward velocity of the skydiver at time t is given by the formula below, where t is measured in seconds, s, and v of t is measured in feet per second. So here's our formula. V equals 180 times 1 minus e to the negative 0.15 t. All right, so that 0.15 I think is going to depend on the drag of what she's wearing, maybe some other conditions about the air. Find the initial velocity, find the velocity after 4 seconds, find the velocity after 19 seconds. So, okay, let's do this one on our calculator. So I'm going to plug that into my calculator. Let's clear out all this mess right here. And that'd be 180 parenthesis 1 minus e to the negative 0.15. So the second key, then the ln key. Make sure you get an e to some power here, not an ln. Negative 0.15 x. And now you got to exit the exponent. Notice I got a little blinking cursor that's in the exponent. So hit the right arrow to get out of the exponent, and then a right parenthesis, and you should be looking like this. We got that? So is that working out okay for you? Now I'm going to assume that we have our table set up correct, so let's just jump over here to table and find a couple values. Wanted to find the velocity after 4 seconds, 81 miles an hour. After 19 seconds, 169 miles an hour. Okay, so that's 2 of those questions. Now I think they want you to round this to the nearest tenth, so I'll call that 81.2. And this is kind of an interesting one. If you round the second one to the nearest tenth, what number should I have in here? Oh. So it'd be 169.6. You know, I was thinking to myself for a second, you know, if you round it to the nearest integer, that'd be kind of interesting, because you get a carry, 169.6, and that'd be miles per hour, miles per hour. But there's one more that I didn't do here, and it's part A. What's going on with part A? How do I find the initial velocity?
Oh, you would just put it at t equals 0?
Yeah, well done. I'm just going to put in t equals 0. Initial means right at the start. And at the start, that means t equals 0. So you can actually do that one in your head. Let's see if we can't do that. Negative 0.15 times 0 is 0. What's e to the 0? What's e to the 0 power? 1. So that'd be a 1. I'd have 1 minus 1, which is 0, times 180. You need your calculator for that part? Yeah, okay. I'm glad to see you shake your head no. Thank you. All right. So yeah, 0 times 180, v of 0 should be 0. Now we can check it on our calculator, but you know, does that make sense? 0? Well, yeah. If you haven't started falling yet, then your velocity should be 0. So v of 0 is 0. All right. All right. Looking good there. Anything else? We okay at this section? Let me just check here. And range. Yeah, I think that nails it. So good on us for section 4.2. Somehow I feel like I should be doing more graphs. Are you comfortable with the graphs?
Yeah.
E to the x, negative 5, or negative x, negative e to the x plus 5, all these things, the shifting around. I mean, I do hope that you understand the basic shapes of these graphs and how they get shifted around. But the bottom line is that you do have a fallback. You can look at Desmos or your graphing calculator. I'm not going to be taking those away from you on an exam. But it's still helpful to know, you know, what happens and roughly what shape to expect. You should be able to predict in your mind and have a good mental image of how these things are going to change. And of course, we practice domain and range in there as well. So I think that's it. We should be good in this section. And if you have any problems with the homework, let me know.